In this chapter, we're going to go ahead and cover the topic of fuel cells. Fuel cell basically is a system that converts chemical energy to electrical energy. It can be regarded as a small chemical factory. For example, in a basic hydrogen-oxygen fuel cell, you have hydrogen and oxygen that enter into a fuel cell, and a process occurs for which it produces electricity and water. So the basic chemical reaction behind that is that 1 mole of hydrogen and a half a mole of oxygen produces H2O as well as electrical energy. So energy is the product of water, the fact that water has a bonding at a lower configuration than oxygen and hydrogen. In combustion, the reaction releases energy in the form of heat, and then that heat is converted to mechanical work, and then the mechanical work is converted to electrical work. Fuel cells are a little bit different in the sense that it takes energy from the electrons as they move from the higher reactant bonds to low energy product bonds. So it's basically done by separating the hydrogen and the oxygen reactants so that transfer is done over a greatly extended length scale. So basically what happens is that the hydrogen combustion reaction is split into two what you would call electrochemical half reactions. So you have the hydrogen that gets split into 2 positive and 2 negative ions. And then what happens is that half a mole of oxygen reacts with the 2 positive ions and the 2 negative ions to produce water. Those 2 negative ions, those 2 electrons, are forced to flow through an electrical circuit and do useful work before they complete the reaction with the oxygen. So it's really 2 reactions. You have the hydrogen that's split into the positive ion and the negative ion. The electron is forced to circulate around an electrical circuit to do some electrical work. And then the 2 positive ions and the electrons come and react with oxygen to produce water. Those half reactions, the hydrogen and the oxygen half reactions, are separated by an electrolyte. The electrolyte allows the charged atoms, the positive ions, to flow through it, but not the electrons. Here's an example of a simple fuel cell. You have 2 electrodes that are dipped in sulfuric acid. So you have one side, the hydrogen reacts with the electrode, and the positive ion goes through the electrolyte, which is the sulfuric acid, flows to the other electrode, where oxygen comes into that electrode, reacts with the hydrogen, positive ions, and then the electrons that were separated from the hydrogen atom, the molecule, and the electrons flow through an electrical circuit, come to the other electrode, merge with the positive ions as well as oxygen to produce water. There are several types of fuel cells. I'm going to basically cover a little bit of an overview of these different types of fuel cells, and then we'll get into a more detailed analysis on their operation. So there are several fuel cell types. A lot of them are defined by the type of electrolyte they have. So the 5 that we're going to look at here is the phosphoric acid fuel cell, PAFC, the polymer electrolyte membrane fuel cell, which is PEMFC, alkaline fuel cell, the molten carbonate fuel cell, and the solid-oxide fuel cell. All of them operate on the same basic principle, but of course, due to the different electrolytes that each might have, there ends up being a little bit different in terms of their resultant output and the amount of heat that they put out. So let's look, for example, at the first one, phosphoric acid fuel cell. You have here the two electrodes, right? The two electrodes on each side of the electrolyte. So the electrodes in this case is a porous graphite. And then here you have the electrolyte. Again, hydrogen comes in, separates into the hydrogen positive ion that goes through the electrolyte to the other electrode. The electron separates, goes through the electric circuit, comes to the other electrode, merges with the positive ion as well as oxygen to produce water. The electrolyte itself is a liquid phosphoric acid, and is contained in a thin matrix between those two porous graphite electrodes with a platinum catalyst. So the catalyst is located at the junction between the electrode and the electrolyte. And the purpose of a catalyst is just to accelerate the rate of reaction in order to produce more current. This particular fuel cell has some advantages and disadvantages. One is advantage is that it's been around for a while, so it's mature technology. It's reliable, and the electrolyte does not cost a lot of money. But the disadvantages is that the electrolytes a lot of times are platinum. I'm sorry, not the electrolytes. The catalyst is platinum, very expensive, and that the fuel cell itself is susceptible to carbon monoxide and sulfur poisoning, and the electrolyte is also corrosive, and it must be replenished. Moving on to the PEM fuel cell, the polymer electrolyte membrane, or proton exchange membrane is another word for this. This is used in a lot of, if you ever heard of fuel cell cars, these would be the type of fuel cells that are located in fuel cell cars. So again, you have a porous carbon electrode, separated by a polymer electrolyte. The membrane itself, the electrolyte itself, is super thin, right? You want it as thin as possible in order to provide the least amount of resistance to the positive ion flow. And of course, it's coated with platinum as well at the junction between the electrode and the electrolyte in order to increase the rate of reaction. The electrode, catalyst, membrane, catalyst, electrode sandwich. So that whole assembly here, right? Starting from the electrode to the catalyst, to the electrolyte, to the catalyst, to the electrode. That's what's called, that's what's referred to here as a sandwich. That's referred to as a membrane electrode assembly. And again, it must be moist in this case. So since it must be moist in this particular fuel cell, the temperature needs to be limited to 90 Celsius so as not to evaporate the water. The advantage is that this thing has a high power density, has good startup since it doesn't have to heat up, and the low temperature makes it good for portable applications. Some disadvantages is that, again, the platinum itself, or the catalyst, is very expensive. Moving on to the next one, we have alkaline fuel cells. The alkaline fuel cells employs an aqueous potassium hydroxide electrolyte. So in this case, you have hydrogen and two OH negative ions that react to produce water and two electrons. On the other side, you have the oxygen reacting with water and two electrons to produce two OH negative ions. So OH negative is conducted from the anode to the cathode in order to be able to facilitate the reaction at the anode. So the excess of water in this case produced in the anode must be removed. So you actually have to remove all the excess of water that's produced in this. And this thing has no tolerance for carbon dioxide. It has an operating temperature between 60 and 250 Celsius. The advantage is that this has improved cathode performance. It has a potential for non-precious metal for the catalyst and has low material costs and extremely low-cost electrolyte. Disadvantage is that in this case, you must use pure hydrogen and oxygen, and then the KOH electrolyte may need occasional replenishment. Then again, you must remove the water that accumulates on the anode. The next one we're going to look at here is a molten carbonate fuel cell. This particular one extracts CO2 in the anode and is consumed in the cathode. So again, you have some extras going on in here in these half reactions. Hydrogen and carbon monoxide reacting to give carbon dioxide, water, and electron. On the other side, you have oxygen and carbon dioxide to produce electron and carbon monoxide. And the carbon dioxide must be circulated between the electrode and the anode, the cathode and the anode. The operation temperature of this particular fuel cell is at about 650 Celsius. So due to the high temperature, it can run on hydrogen and simple hydrocarbons such as methane and simple alcohols. And since it runs on a molten electrolyte, it is better suited for continuous power applications. So this has a great advantage in fuel flexibility, also in non-precious metal catalysts, and it has high quality waste heat. Since it operates at 650 Celsius, it could be great for cogeneration applications. So disadvantage is that it must implement CO2 recycling, the molten carbonate is corrosive, and you have degradation lifetime issues, and the materials are relatively expensive. This last fuel cell, solid-oxide fuel cell, employs a solid ceramic electrolyte. In this case, water is produced at the anode, and the anode and cathode are made from different materials. This particular fuel cell has an operating temperature upwards of around 1,000 degrees Celsius.